So I will ask you more questions and we'll discuss rather than me presenting. Okay. So Sachin had posed a question last week that uh, if we have very complicated systems like 4 or 5 elements in the system, then is there any chance that it will form a metallic glass? Right, Sachin?
Okay, just now he went outside. I think wait for 1 minute. Meanwhile, you can discuss other things.
What happened?
Sachin just went outside, so
Are you able? You are not able to hear us?
I can hear you.
Okay.
yeah, Sachin.
Sachin is
Sachin is
asking.
waiting for you.
Oh, wait. He is asking one question.
Last time you asked one question.
Last time you asked something, right? Yeah. What is that? Just a minute. Huh?
Okay, I will tell you. I mean, if there are 4 to 5 elements, will they form bulk? I mean, bulk metallic or something?
Sachin, can you repeat your question?
Yeah, just a minute. Despite the random distribution of atoms, high entropy alloys are structurally ordered. So,
Yes. Yeah. So the question is that if we have a high entropy alloy system, that is, if we have 4 or 5 different elements, different chemical species in the system, then why do they still form a simple crystal structure? Even though they each of those individual elements may have very different crystal structure, maybe BCC, FCC, HCP, but when they are mixed together, they generally form very simple crystal structure and does not break the symmetry of the lattice or the crystal. So I will explain a little bit of disordered, partially ordered, ordered and metallic glasses from a crystallographic perspective. So how do you define a crystal? So crystal is it's mix of two things. One is lattice and one is basis. So when we say lattice, it is like a mathematical concept. It doesn't have any physical significance. It just says that okay, we it's a what happened?
connection loss. So it will be lost over time and again. So no worries, you can continue. It will be recorded. No, no.
No, I am hearing you connected, disconnected something, I guess.
Yeah. We got disconnected. Can you go back?
You can start from this slide.
Yeah, this is the first slide.
Okay. Okay.
So can you see the equation? Crystal is equal to lattice plus basis.
Yes. Yes.
So lattice is actually a mathematical concept where you actually define how to repeat something in a 3D space. For the ease of explanation, I'm keeping it 2D, but you can easily imagine it in 3D. So and lattice means how a set of atoms are arranged in a 3D space, and basis is actually how at those individual points what will you put. So in this particular slide you can see the basis is a circle and square. You can say circle is atom A and square is atom B, like that. So this set of two chemical species becomes a basis, and this basis is put at each of these individual cross points in this matrix on the left hand side. So that's how you get a crystal where at each of these cross points this basis is repeated. So is it clear so far? A very simple definition of crystal.
Yes.
So here I intentionally choose two different elements. Even if you remove this square, then also it will still remain the crystal, because now it will become a basis has only one atom. Here I have intentionally chosen basis to be having two atoms. Okay, clear so far?
Yes, yes.
Okay. So let's go to order and disordered crystal. So in ordered crystal, you can see on the left hand side, every circle, let's say I take this circle, is surrounded by 4 different squares. And every square is surrounded by 4 different circles. Meaning every atom A is surrounded by 4 B atoms, and every B atom is surrounded by 4 A atoms. This is called an ordered crystal. Ordered crystal meaning the chemistry is same everywhere and the crystal structure is also same everywhere. You can see it is still square. This square, if you imagine, this square is same everywhere. And the things which are present inside that square, that is these circles and this rectangle, are same everywhere. I chose circle as my corners of the square. Even if I do it like this, then also it's same. Is it feasible?
Yes, yes.
Yeah. So that is so the way I'm intentionally keeping it square for easy explanation and easy visibility is every atom has equal number of other atom of a different element. That is the neighbors are same everywhere. The nearest neighbors. The environment is same everywhere. So now this thing, when it repeats in 3D space, then also it remains the same. When you put so what is the example of this is an intermetallic. You can say Ni3Al. Very simple example. You have how is it four total 4 atoms in the crystal, and then one aluminum atom is surrounded by 3 nickel atoms. As simple as that. A simple formula. The chemistry is same everywhere, and the crystal is also same everywhere. Is the ordered part clear? Because there are two things. One is structural order, and the other is chemical order. So in the structural order, we are keeping it square everywhere. That means we are keeping the lattice same everywhere. And the chemical order, that means that every atom has same nearest neighbors, same number of nearest neighbor, and same type of nearest neighbors. Is it clear so far?
Yes.
Okay. So when we go to disordered, you can see the chemistry may not be same everywhere. You can see for this rectangle, there are 4 circles. But for this rectangle, there are only 3 circles. And one another rectangle, one other square. And again, for this circle, there are 3 circles as first neighbors and 1 square as first neighbor. You can see I intentionally kept it on the same grid, same lattice. The crystal is same everywhere. It is still cubic crystal, cubic lattice, sorry. But the chemistry is not same everywhere. So every circle is not surrounded by same number of squares, and every square is not surrounded by same number of circles. So that is a very classic example of alloys. You can say steel, brasses, super alloys, like that. So again, I repeat, it has so in the disordered system, the crystal is same, meaning the structural order is present, but there is a chemical disorder. Clear? The very simple difference between ordered and disordered.
Yes.
Now, when I go to partially ordered, there is a structural order in it, meaning it is still square. It is still square everywhere, but chemistry is not same everywhere. There are local regions where the chemistry is same. You can see this dotted rectangle where every rectangle has 4 circles. I'm giving very crude example, but when you put it in HRTM, you will also see something similar only. You can see in this square local regions where every A atom is surrounded by 4 B atoms, or vice versa. I mean, giving very narrow region of local chemical ordering. So this is called a partially ordered system. So the chemistry here, see, the overall chemistry in this region is still, you can say, AB, where there is a 1 A atom and 1 B atom. But there are local regions. Let's say if you look at this region, there are total 1, 2, 3, 4 A atoms and 1 B atom. Same like this here. But in this region only, there is the chemistry is A1 B1, meaning 50% of A and 50% of B. That means here it has partial chemical order. Overall, the structural order is same everywhere. So there are these 3 things are clear: ordered, disordered, and partially ordered. Is it clear so far?
So then, I have a doubt.
Yeah.
We're still not able to make it out for between disordered and partially disordered. Means, how can you comment on the structure thing? Uh, how is it distinct for disorder and how is it for partially disordered system?
Okay. I'll repeat the disordered part. See, in disordered, every lattice point will have a different chemistry. Every lattice point will have a different environment. So this, when you say this disordered crystal, it's a very ideal state where it is cube. Let's say square everywhere, but what's happening? Hello?
ఎప్పుడు అంతే ఎవ్రీ టైం
Same thing is happening here. Only for us it's the same. No. It is everywhere.
What happened?
Connection is getting lost.
It's particularly when
Oh, because my internet is good.
Problem is in Google Meet, I guess. It's happening every time.
Okay, then what you do is you can switch off your video. Maybe that will save the bandwidth.
Okay.
Okay. Okay, so Pradeep was asking that what is the difference between disordered crystal and partially ordered crystal? See, disordered crystal is a very ideal state where the crystal structure remains the same. That is, let's say it's cubic or rectangle or cubic, you can say, or square. And every corner, let's say this corner of this cube, will have a completely different environment surrounding it. Then only it is called as completely disordered crystal.
Okay.
You may say, I will look at only one square here and I will say that it has a partial order or partial disorder. Correct?
Okay.
Yeah, but if you repeat it in 3D space, disordered crystal has a very simple definition that every lattice point will not have same environment surrounding it. No matter what you do, you will still find some partial ordering, but we intentionally do not call it partially ordered or partially disordered system, because for to call it like that, you need to have a certain, let's say, you need to have enough number of atoms surrounding it where there is a local region where the chemistry is same everywhere. That's why I intentionally here there are only one or two squares which are same, but in this I expanded it a little bit, and this is the region which I kept it as partially ordered. There is very what I mean is, a disordered system is a rarity, meaning no matter what you do, you will still find local regions where there is a partial order will be present. Have I answered your question, Pradeep, or you are still confused?
So the disordered system is like a very ideal case. It may not exist in real life, but partial ordering is something which can exist.
Yeah, partial ordering is the only thing which you will see everywhere. You will never see completely ordered crystal, you will never see completely disordered crystal. You will always see somewhere in between. But in the case of intermetallics, in the case of let's say ceramics, you will mostly find because in ceramics you need to maintain charge neutrality also. You say that TiTin what you are working on, or what Varalakshmi is working on. TiTin, you will always have TIN everywhere. If you're talking about TIN, if you say it is TIN, it will be TIN everywhere. If there is a nitrogen missing, there has to be a titanium missing to maintain the charge neutrality. So that's a different story. But ordered crystal is mostly ordered crystal. When you say, it's mostly intermetallics. And disordered crystal is a completely other extreme. But yeah, for alloys, they are accepted as they are disordered. They are chemically disordered. Structurally, they are ordered. BCC alloy, steels, stainless steel FCC alloys, super alloys FCC, brasses, they can have different crystal structure. Duralumin, our airplane bodies, they have also something different crystal structure, like that. So these are the two extremes: ordered crystal and disordered crystal. Mostly you will have whenever there is an ordered crystal, somewhere some local angstrom region will be partially disordered. If it's a completely disordered crystal, somewhere some local angstrom level region will be partially ordered, vice versa.
Sophia,
Yeah,
SQS falls under which category among all of them? Partially ordered or disordered?
SQS. The answer is in the name itself. It is special quasi-random structure.
Quasi-random.
Quasi-random structure. So it is random, but it's quasi-random. Can you say why it is quasi-random?
Yeah.
What you can do is you can switch off the mic from Pradeep's keyboard, computer, I guess. Hello?
It is from Sachin.
Hello.
Yeah. Yeah. Can you switch off all your mics and keep only one mic active?
Only one mic is active.
Okay, I was hearing echo. Okay. Yeah. So, what was the question?
SQS falls under which category?
Yeah. So SQS will falls under actually. It will fall under disordered system only, but it will have a little bit of partial ordering. So to prevent that partial ordering, we say that we need to have very big cell, big supercell or big slab to prevent that ordering happening. SQS, you can safely say it's a disordered system. But I was saying that the answer is in the name itself. It says quasi-random. What does that mean? We all understand periodic boundary condition.
Yeah.
Yeah.
Yes.
So let's say this is a 64 atom cube, which let's say you are working on. There is A atom here. Uh, there is A atom here, and if there is a A atom here, and then there is B atom here. Let's okay. I'm just giving an explanation. Now there are 64 atoms in this. Since it's a periodic boundary condition, what do we say? This entire thing will be repeating here also, correct? And this is repeating here also, and here also. Here also. Now I'll just talk in this direction. See, A is so B is here, so this B will come here. This A is here, so this A will come here. And this A will come here. This A will come here. This A will come here. This B will come here. Now, since it's a periodic boundary condition, at the boundaries, at least at the boundaries, you say that there is a BA kind of thing happening. Correct? So that's why it is called quasi-random. I am talking about. Hello.
Yeah.
Yeah. So I'm talking right now. I am explaining only at the edges, at the boundaries of the slab. That this will lead to the partial ordering. This is one case. The other case is in the SQS, inside of the SQS itself, you will not find a like complete randomness. See, now let's say there is an AB kind of thing. Now, if you look at this region, you can say that in this region, the chemistry, the stoichiometry is A to B. Correct? There are two A atoms and one B atoms at the center. So if the SQS is big enough, then you can say it is partial, it is disordered system. But we never say it like that, because what is your property of interest that decides whether your SQS is right or wrong. If your property of interest is, let's say, enthalpy of formation, and that enthalpy of formation is very very far off from experimentally observed enthalpy of formation or any other reliably calculated enthalpy of formation number, then you can say that your SQS is not the correct representation of reality. Are you getting what I'm saying?
Yeah.
We never say that the SQS is right or wrong. If the SQS is able to model reality correctly, then we say that that particular SQS was right. Everyone accepts that there will be local ordering happening inside the SQS. If the SQS is big, let's say if the SQS has 128 atoms, and if it is able to capture the correct enthalpy of formation, if that is what you are looking for, then we can safely say that SQS is the correct representation. Hello, hello.
Ah, yes.
Yeah, I think it is getting disconnected multiple times.
Yeah, there is some issue with the Gmeet, I guess.
Or lose contact maybe.
Contacts are good, but there is some issue with Gmeet itself.
Every time.
Maybe there are speakers.
Maybe you can disconnect something. Hello.
Ah, yes.
Yeah, there is an echo.
Just a minute.
What you can do is you can keep you can use the mic of a mobile phone and speaker of the maybe the big screen.
Okay, you are good to go. Thanks.
Yeah. So yeah, that's what I'm saying, that if the SQS is big enough and if it's able to predict the property of interest correctly, then we can safely say that the SQS which you are using is right. Everyone accepts that there will be local ordering inside the SQS, but that ordering is compensated by sufficiently large disordering inside the SQS, so that they are cancelling out each other and we are saying that okay, SQS is correct. That's how we say. We never say the SQS has complete disorder. No, because the name itself is says that it is quasi-random. It's never perfectly random. If it has to be perfectly random, what should be the size of the SQS if it has to be perfectly random?
Infinite.
Yes, because it will be repeating somewhere, right? It's a periodic boundary condition. Even if you take 1,000 atom, the next atom after the 1,000th atom will be repeating, will be the mirror image of the first atom.
Correct.
So we never say that S2S is completely disordered or completely ordered. Yeah, if it is completely ordered, then it's an intermetallic. Then why you are using S2S? So but the beauty of SQS is it is able to predict many properties accurately, and you have the freedom to make it partially order as well. The way the TI study you are doing who is doing the metal ceramic interface guys.
Power on. Bluetooth mode.
Okay, so far so clear. So did I clear a doubt that whether the SQS is completely ordered, completely disordered, or partially ordered?
Yeah, it was clear. Correct.
Yeah. So so never even write like that SQS is completely disordered.
Okay, got it.
Yeah. Yeah.
I had one doubt also. Like, is it an accepted fact that intermetallics are ordered?
I gave an example of an intermetallic which was an ordered system, that is Ni3A. I do not have any example which says that we can have a disordered intermetallic also. But generally, what my understanding is that most of the intermetallics are ordered only, meaning they have chemical order as well as they have structural order. So Ni3L is a very like classic example of an ordered system where nickel is at face centers and aluminum is at body corners. Any other question?
No.
You can go ahead.
Right.
Okay, now metallic classes. So that was the main question, that if we have so many systems inside, then what will happen? So I'll just first explain what is metallic classes. Metallic classes has no crystal structure and they does not have the same chemistry everywhere. You can see this figure on the left hand side. Can you see any crystal structure here? If you try to draw.
No.
Just for the guidance, I will draw the matrix. I will draw the lattice. You can see every circle may not be surrounded by same number of squares. You can see here the nearest neighbors. I mean, see this particular circle is surrounded by 2 squares and 1 circle. This particular circle, its first nearest neighbor is all 3 are circles. So for metallic glasses, there is no crystal structure and there is no chemical order. Okay.
Okay.
So this is a very simple definition of a metallic glass, you can say. To achieve, to call something a metallic glass, first thing is it should not have a crystal structure. If it is a crystal structure, then you cannot call it as glass. And to make something into a glass, you need to have very, very high cooling rate. This is a very prime requirement. You can see the cooling rate 10 raised to 7 Kelvin per second. We're talking about 10 million Kelvin per second, meaning it needs to go from 10 million degrees Celsius to zero in 1 second. If I put it like that. To achieve metallic glass, because when we are manufacturing metallic glass, it is manufactured from a liquid state, a molten state. When there is a molten metallic alloy, let's say, is present, and now you want to cool it, it has to go through nucleation and growth. If you want to suppress that, that is the nucleation of second phases, a nucleation of crystalline phases, then you have to have very, very high cooling rates. And this is the reason when we have high entropy alloys, they do not form into solidify into glasses, because the cooling rates are not large enough to overcome these nucleations. Any questions so far?
No.
What is the crystal structure of a liquid? Let me ask this question.
No. Liquid has no crystal structure.
Hmm? Yeah, I mean, there is no crystal structure, we can call it amorphous. Metallic glasses are also called as amorphous. So when you want to freeze that liquid as it is, without letting any, see, in this figure on the left hand side, this figure, if I shift this atom slightly here, then it will fall into the lattice position, right?
Correct.
If I fix slightly move this square here, then also it will go into its lattice position. This one, if I put it here, this one, if I put it here, like this one, if I put it here, meaning every atom, be it square or rectangle, can go to a nearest lattice side, correct? The distances are very, very small. Now, if imagine if this distance is, let's say, 3 angstrom, then this distance is hardly 1 angstrom or even lesser than that. See this distance. So to prevent that thing, you need to have very, very high cooling rates. Otherwise, if your cooling rates is not large enough, the atoms can easily go into their nearest lattice sites, and then they will form a crystalline system. Then they may form an alloy or an intermetallic. Then they may precipitate into a crystalline phase. To prevent that, we need to have very, very high cooling rate. Is it clear so far?
Yes.
Yes. Then so metallic glasses we can convert into pristine materials by annealing it. Is it right?
Yes, 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 yes. Because the moment you give them the energy, they will easily diffuse into the nearest lattice site, and then it will be a crystalline state. There are studies where you keep a metallic glass inside an XRD, you do high temperature XRD, suddenly you'll start seeing the XRD peaks. Meaning now it has transformed from an amorphous state to a crystalline state.
Okay.
So far, so good?
Yes.
Yes.
Okay. Now we'll go to high entropy. So there are many definitions of high entropy alloy. I will take the very basic definition of high entropy alloy. You need to have so to call an alloy as high entropy alloy, the classic definition is the system needs to have 5 or more different chemical species, that is 5 or more elements in 5 to 35 atom percent composition. Now imagine a situation where you have B, C, D, P, Q, L, M, like so many different elements. Now they are mixed together. Imagine titanium, zirconium, hafnium, chromium, moly, rhenium, ruthenium, zirconium, polonium, all are mixed together. Now, when these so many systems are mixed together, having completely different crystal structure, HCP, FCC, BCC, simple cubic, then they are mixed together. Then don't you think that they should form into a disordered state, because everybody will try to go into its own crystal structure, parent crystal structure? Yes or no?
Yes.
Yeah, but that doesn't happen. Why? Same reason. This is the one. Imagine this is titanium, this is zirconium, this is maybe copper, this is boron, maybe this is tantalum. Same logic applies. They have to make them crystalline, they need to travel very small distances, maybe 1 angstrom or less. See here, this copper is already at the lattice side, but this tantalum can already easily go this position and become a crystalline state. So the way high entropy alloy systems are synthesized is mostly by mechanical alloying, then spark plasma sintering, or by arc melting route. If you open my drawer, there will be two small bottles. It will have molybdenum tantalum tungsten and molybdenum tantalum tungsten vanadium. You can see how will they look, the arc melting buttons. I had synthesized them 4 or 5 years ago. What I mean is the synthesis route, that is mechanical alloying then spark plasma sintering or the arc melting, does not give very high cooling rates which are required to form glasses. That's the reason high entropy alloy, if you want to make their glasses, you need to have very high cooling rates. But since there are so many elements in large fractions, and every element is still trying to go into its parent crystalline structure, they will slightly distort the overall crystal, which is I have shown here on the left and right hand side. Left hand side is simple. Let's say it is, imagine this is FCC. We have all atoms at the face, and then since now every atom is trying to distort the lattice, now it is no longer alpha A, rather than maybe it is every side is different, A, B, C, and these angles are also different, alpha, beta, gamma.
The RMB is measured with respect to this ideal lattice.
Yes, but still the way we say it is lattice has been distorted, that does not mean the lattice has completely broken, the symmetry has broken. No, let's say this is one lattice. It's getting very, see, this should have been the ideal state, correct? Every atom perfectly at the intersection of these lines, correct? But reality is not so ideal, so this atom will be slightly shifted. Instead of being at it will be slightly shifted. Instead of being at the center, it is now off center slightly. So every atom can still be identified by its very near lattice position, and since it has been moved from its ideal position slightly, so that leads to the lattice distortion. And this lattice distortion is present in everywhere, meaning every system, binary, ternary, quaternary, quinary, everywhere. You don't even have to go to very, let's say, 5-component systems such as high entropy alloy to observe this lattice distortion. The moment a second element comes in inside the lattice of inside a parent lattice, locally there will be a lattice distortion. Any questions so far?
No.
But did I answer your question that why entropy alloy do not form into classes?
Yeah, now it.
So basically, it is the lattice distortion which is affecting it, but the symmetricity remains everywhere.
Yes.
Yeah, that's
The
the
lattice
answer to his.
come again?
That's the answer to his question, right? He just was asking that. Yeah, because
Right.
No, his question was why entropy alloys do not form into classes.
oh, okay.
Why there are so many elements here mixing together, but they do not form classes? Because you need to have very high cooling rates, more than million degree Kelvin per second, to prevent these atoms going into nearest lattice site. And the diffusion distance are very small, angstroms to picometer. And the surprising thing is, most of the people who are working in high entropy alloy have come from the metallic glass research, bulk metallic glass research. Professor
Oh.
B.S. Murthy was also metallic glass person before he shifted to high entropy alloy. You just change the cooling rate, you have a glass, you make the cooling rate slow, you have a high entropy alloy.
So anything can be made either into high entropy alloy or metal.
Yeah. There are, of course, you need to have, so the barrier to form something into hollow, glass or not is that cooling rate only.
Hmm.
So if you have a setup which can give very high cooling rate of million degree Kelvin or more, you will easily form anything into glass. That's why whenever there is a bulk metallic glass, you will only find them in the form of thin sheets, not as bulk component. Thin sheets, like maybe slightly thicker than aluminum foil, because you pour a liquid element on a very large rotating wheel which is water cooled, so get very high cooling rates. So is it clear that why entropy alloy don't go into classes?
Yeah, it's clear.
And is the difference between ordered, disordered, partially ordered clear?
Yeah.
Okay, this is the last slide. Yeah.
Okay. Thank you.
Yeah, so that's what I had written.
Yeah.
If you take very complex HEA and cool rapidly, you'll have high chance of going into class. There are a lot of other things. Phase diagram, you have to look, it has to be deputatic, blah, blah, blah. But the simple logic is, if you cool it fast enough, it will form into class.
Got it.
Okay?
Yeah. Thanks.
Okay, bye-bye, everyone.
Bye bye. Recording.